if socket set here, so we have our socket set, SDLnet underscore free socket set here, socket set, close parentheses, semicolon. Okay, what on earth is this? Okay, so basically what we're saying is if there is data in this socket set, alright, and I'll just go ahead and, if data in socket set, then remove that data from the socket set. Okay. And that's basically what's going on there. So basically we're saying, hey, if there's junk laying around in the socket set, we need to get rid of it. And that's exactly what we're doing here. So we're just removing it. And now we're going to actually fill it with actual good data that actually matters to us. And so we're going to say SDLnet underscore alloc socket set here, open parentheses max num clients plus 1, close parentheses semicolon, because we have to do a plus 1, otherwise it'll be off on the numbers. And that will allocate enough spaces in our socket set to hold all our clients. In this case, it'll be 17 that gets in there, because remember, max num clients was 16, and then add 1 to that will make it 17. And then this will create a socket set with 17 openings there for it. Alright, very cool. If, I'll just leave this up a little higher so people can still see if they're copying this. So if open parentheses not socket set, close parentheses, open curly brace, sorry, I like it that way, print F here, so I'm just going to display it to the screen, in quotes here, SDLnet underscore alloc socket set colon %s/n close quotes here, comma SDLnet underscore get error open close parentheses semicolon. Alright, so we're going to say if you're not able to create the socket set, if there was an error in creating it, it ends up being an empty socket set, then we were unable to allocate the socket set, and here's the actual %error value of that when we go and get the error. And we're going to exit with a value of 1 from the program, letting us know that, hey, this thing exited with errors. So in which case, you know, most of the time this can be a major error. You know. So yeah, most of the time that's a major error if that goes down like that. Alright. Then we use SDLnet underscore TCP underscore add socket, open parentheses socket set, comma server socket, close parentheses semicolon. Alrighty. So what's going on with this? Well, it's a lot more simple than you probably think. So SDLnet underscore TCP underscore add socket. This command adds a socket to our socket set. We passed in our socket set to let it know what socket set we want to add a socket to, and then we pass in what socket we want to add to the socket set. In this case, our server socket. So we need to add our server socket to our socket set, and that's the first socket to get added to our socket set. Okay. And then I did an app quit equals false. Right there. And I just did this for testing purposes so I could see the length of, well, don't worry about it. So what we're going to do now is wait for a connection and send data and then terminate. So, terminate. Alright, so I got this into a while loop here. So while open parentheses, exclamation mark, app quit, close parentheses here, open curly brace, just check for a server socket if there is a pending connection. If there is one, accept that and open a new socket for communicating. fprintf standard out, checking for clients here. And I did that right here so I know to myself that I'm looking for clients. So that way I can see where I was in the code for testing purposes. Okay. So if open parentheses client temp dot socket. Now remember I was talking about client temp earlier. This is where we're going to set up and make sure everything went through properly with our client before we add them to our client list. Because I'm not interested in having a client that didn't properly connect or something happened to get added to our client list. And not to mention, in order for it to get added to the list, we need to have the entire structure laid out and filled out before it's added. Otherwise, we have a partially added whatever, which isn't going to work. So in order to make this work with the lists, the way lists work in C++, for a standard lib library, and to make this work in a logical manner for network connectivity, then we need to set this up appropriately. Okay, so we're going to do client temp.socket equals SDLnet underscore TCP underscore accept. Alright, so basically we're saying we're accepting a connection on what? On the server socket. So if we received a connection on our server socket that we had earlier, that we set up above, then that gets assigned to our client temp.socket. So we're going to be assigning that value to our client temp socket. Alright, so we received a new socket from a client, basically received a new client trying to connect to us, and we accepted that connection. So it's getting stored into the socket, and the reply is going to be what socket it is. Alright, so now we can communicate with the client using the client socket. Server socket will remain open, waiting for other connections. So now we're going to get the client's address, though. So we got the socket, but we need the address. So how do we get the address? So if open parentheses client temp.ip equals SDLnet underscore TCP underscore get peer address here, open parentheses client temp.socket close parentheses close parentheses close parentheses, then that's going to get us our IP address from our client socket. So we know what the socket is for our client, and then using this function right here, SDLnet underscore TCP get peer address, is going to get us the IP address we're looking for. And of course, when we get the IP address, we also get the port. So great. Of course, this is all going to work on the server port with 7770. So print the address, converting in the host format. Okay, so now we're going to get into this, and this is going to get into some binary operations in order to get the address into a human readable format. The way it is now, it's just a jumble of numbers that's totally unreadable to anything but the computer. But we want to be able to read it in standard, easy to read format. So the way this is going to work, because I mean if you look at it right here, what we want it to look like is this. The way it actually looks right now is something like that. I'm sorry, something like that right there. And be able to read this as that is quite, no one can do that. No person can do that, right? But what we want to do is convert this into something like that to where it's readable. Because right now it's not readable. Okay. And I can prove this to you if you like. I mean, we could set this up where we have the client and server both running on here, and then connect them up, and then you can see the difference between the two, with it not connected and with it connected. So, I mean, it'll take a lot longer to do that. Basically, like I said, it'll just come out like a number like this. If we don't, it literally will just be something like that, without the T, of course, without any numbers. It'll be just some number like this, and we need to make it look like this. This is what's going to happen if you just display the IP address from here. So that's not going to work, obviously. That's not readable. So we need to make it readable. Went to the wrong place. Alright. Let's make that readable. So what I'm going to do is I'm going to extract this particular value here. And I'm going to load it into IP convert. So right now we have client temp.ip and then arrow here host. Alright, so where did arrow come from? Okay, let's explain where this little arrow came from C++. What we're doing is we're dereferencing this part. And then we're getting to the reference part to here, so we're pointing to this memory address where this data is in RAM. So we need to make this not a pointer for this part here, dereferenced, and then to make this part a pointer to point to this data in this structure. So that's important. Otherwise we won't be able to access it. The way this would have to be written otherwise is quite painful. It'd have to be written like parentheses here, client temp dot IP dot host, like that. Oh, sorry, IP hosts, like that. Otherwise, so that's kind of complicated and difficult. So because this happens and appears so often in C++, they ended up just adding this little arrow right here, which takes care of that whole setup, so you don't have to ever type it out like this. So that way, because this would be dereferencing this, where we're converting this from pointer to just data. So we're accessing just the data aspect, and then we'll be accessing the pointer allocation part of that there. Okay. Awesomeness. Okay. So the way this is going to work, I don't know, I might just show you guys real quick what it's going to look like if we didn't do this. Let me just set this up real quick where I show what it looks like without doing this correctly. I'm going off script here. I shouldn't do this. I really shouldn't do this. It's prone to more likely to have a mistake than not have a mistake by doing this. Alright. So say I had something like that there. So hopefully everything gets read out correctly. Let's see here. Yeah, sorry, wrong thing. I need to double click on net chat server and compile that, please. Alright, there we are. Checking for sockets ready. Now I had that up a bit above earlier. Where was that? That is... Oh well, it's up here somewhere. So we're going to be checking for the sockets that are ready. And basically, we have the IP address over here. If I could get pull up, please. Alright. So we got our IP address here. If I hold down Control, Shift, and then hit C, I can copy that. Okay. And then if I come over here, actually click in there, I can connect to it. So if I can remember my password, that helps even more. Alright, so I just need to get to where this is being located at. Network client test, I think. cd into bin, cd into debug, plus network client test space 192.168.1.129, I think. Let me double check that is correct. No, it's .11. Okay, that's where it's off. Alright, so it's 11 right there. Okay. And then a port is 7770, like so. Hello. Server says hello back. Awesome. Now, if I come back over here to my server and pull up the application that we now created here, check it out. host connected, blah 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 number. Oh, that's really not readable. See, but that is the number that's actually there for the IP address. We have converted this number into a human readable 192.168.11.132, which is our other ones, our client's computer's IP address. So you can see the difference between this number right here, which is negative 10627288828. I mean, my gosh, good luck figuring that one out, right? And 192.168.11.132. So those are the same number. It's just that this has been extracted into human readable form. So how do we extract this into human readable form? By playing with the bits. Alright, so let's get into how to do that. And I'm just going to go ahead and kill this real quick here for the server. Because I don't want that running. I just did Control-C to kill it. I'm going to do the same thing over here on the client side because I don't want it continuously connected. Quit. Alright, cool. It quit. Oh, yeah, just real quick so you can see that easier. Yeah, so you can see what happened. It all went through correctly and all this. Alright, cool. Let's bring this one back up. Alright, so as you saw, that was that weird negative number here, as it normally is. And then we converted it over here into a readable number. So obviously went through the trouble. Luckily I managed to code that without making a single mistake on the fly here, thankfully. But let's go over how we're going to do this bit order operations. Alright, so let's go ahead and hop on that now. What we need to do is reformat this. So fprintf here, std out, comma, host connected, colon, %d dot %d dot %d dot %d space %d slash n. Okay, what on earth is all this stuff? Okay, first of all, let's get into what we're doing here. So this first part is the first number from our IP address. So as a for instance, it'd be this number here, right? And then the next part of this code is going to be the next %d, if I can get my highlighter, right? And it's going to be the next number. So you see the dot here? Notice the dot that corresponds between it. See the dot? There we go. Same thing. So basically we're just putting it out in the same format as what you're seeing here. And we're going to extract this data here bit by bit. And then the next %d, if I can get it to show up, be this one right here, so on and so forth, getting outputted to the screen. Okay. And then the last %d is going to be our port, right here. Okay, so the other part here, we have the IP convert equals SDL underscore swap BE32 over here, open parentheses, client temp dot IP here, and pointer to the host, close parentheses, semicolon. Alright, so basically we're grabbing this data here and putting it into an IP convert where it's swapped for the order of the bytes to where it can be extracted. And of course IP convert again was in the proper format to make this possible. So what we're going to do is an IP convert greater than symbol. And what this is a bit shift operation. Now if you remember right, and this gets into binary operations, or ones and zeros shall we say, within the computer. On off, high low voltage, however you want to say it. It's all the same thing. So basically what we have here is this IP convert, and if you remember right, this is a 32-bit integer long unsigned int variable. And here it is here. Yep. Unsigned int 32. So that's cool, because what we're going to do is we're going to shift it over 24 bits, which will only give us 1 byte, and it'll be that first byte that we're looking for. We're going to shift it to the right hand side, and I have a little program to basically prove that this works. So I just read this really short thing. I mean, it's short, and I made this 2 byte long variable, but you'll get the idea regardless. And you'll get the idea across. Alright, so first off, let me just save right here. I'll double click this, make sure this is set up for compiling. And you see it runs when we get 56,580. I'm sorry, 780. Okay. Well, wow, that doesn't look anything like the hexadecimal value of DDCC. And I put the 0x in here in front of it in order to do a hexadecimal value. If I don't do that, then it won't come out as hexadecimal and we'll have a type mismatch. But if I do it this way, it knows it's a hexadecimal number. In order to aid us with this problem, I have set up, pulled up this wonderful address, http://www.easycalculation.com/hex-converter.php. And what this does is let's put us in a value and kick back out what the decimal value is and the binary result is. This will help us understand what's going on. So check it out. DCC, or right here, is going to be 10, 10, and hexadecimal. These are 10s for the D's. The C's here are going to be 11s. I'm sorry, not D is not 10. A, B, C, D. Yeah, it's way higher number. A is 10, B is 11, C is 12, D is 13 for each one, and the C's are going to be 14s. I mean, not 14s, but they're going to be 12s. And then E is going to be 14, and an F is 15 for each number. And F in binary be straight ones here, so it'd be a quad of ones. I'll prove that to you real quick. Here's an F. See, there it is in 15, and there it is all in ones. And I could even prove it to you for each one. You see, E is 14, D is 13, C is 12. B is 11, and A is 10, so on and so forth. And then you just have your regular numbers in hexadecimal. Alright, DDCC, just to prove a point. And so you'll notice it's the same number as what we have over here when I run this application. So it is 56,780. Awesome. Great. Now let's see what happens if we shift this bit over. Alright, we're going to shift it to the right. 221? Okay, what's 221? Let's find out. Well, what if I told you it was CC? It's not, it's DD. I'd be lying if I said CC, right? It's going to be DD. And the reason it's going to be DD is this is getting shifted to the right, which means that the CC is getting pushed off of our bits. So, check it out. I'll explain this a little better. Right, so you see how we have this set of binary bits, right? So the DD, remember, each letter takes up 4 bits, right? So DD is going to take up an entire byte, whereas CC is going to take up another byte. Now, with the number we're working with currently in that little demo program there for showing the bit transactions here, it's only actually 2 bytes long. So that'd be essentially the same thing as this. So if we count out 4 bits, that'll put us there. That'll be the first D. And then the next D is going to be this set right here. And check it out. We got 8 more bits going across here. So if I shift this thing 8 bits, because that's what that 8 means right there. Okay? That's what this 8 means. Shift 8 bits to the right. Okay? So if I shift this 8 bits to the right, this is going to get replaced by this number right here. It's going to simply be wiped out. And then the rest is going to be filled in with zeros or whatever. And then you end up with just DD and nothing for the rest of the number. Okay, so that's what happens there. Okay, so that's how shift to the right works. If I did shift to the left, it would do the opposite of that. It would shift the bits to the left, 8. Now I want to do an and equals here 0xFF. Now, let me explain this a little bit. This is 204. 204. Now, that looks familiar, doesn't it? So that's CC. Check it out. 204 for our decimal value. Awesome. Well, real simply, that's 1100, 1100. Okay, wait a minute. Now, how did we get that? Well, it works real simple. This is a binary AND conditional setup here. And so it starts going from the right and goes over left. You're going, well, why does it go right to left? Well, it makes a whole lot of sense, because that's the way numbers go, basically. And binary numbers are no different. You start counting from the right-hand side over to the left, opposite the way you normally read. Same thing goes with your decimal numbers here, right? 4 becomes for the 0 before the 2. So this is the lowest value here, going up higher and higher. Same thing goes with a binary number. Lowest value all the way up to highest. Same thing, no different. So when we're doing FF, remember it's 111, we're doing our binary AND. And the way a binary AND works is over here. It's the way, best way to describe this. Now we have an AND, NOT, OR, XOR, and we have the AND here. And then of course we have our bit shifting too. And here you can see the left shift and the right shift here of what's happening with the numbers here. So yeah, check it out, we get zeros left behind when we shift it. And I mean, this is cool. And different symbols make it do different things. Like AND is, for instance, the ampersand, OR is going to be the vertical bar, and then you can do the caret symbol, and for another one, and you know, so on and so forth. And NOT is going to be the unary symbol, where it's like, oh, okay, let me show you. OR is bitwise OR. This is the bitwise AND. This is the XOR, exclusive OR, and then this is the unary NOT, or shall we just say NOT. Okay, so that's how you do bitwise. Those are all the different bitwise operations there. I have it pulled up on one of the web pages. I can show you here in a bit. All right. So what happens here? Well, check it out. AND works in a very particular way. And let's have a look at it from a binary standpoint. It's only going to keep it if both sets are 1. Anything else other than 1 is basically end up being a 0. So if you end up with 1 and 1 together in the same category here, you end up with a 1. Anything else, see 0 and a 1 here, it's going to be a 0. A 1 here and a 0 here is going to be 0. And a 0 and a 0 is going to be a 0. So essentially, this is going to keep only that matches. Now, we filled it in with 1s, right? Because it's FF here. So that's straight 1s. That means anything in there with the straight 1s is going to get preserved. So I can prove that to you real quick. Check it out. FF is going to be 1 whole byte of 1s. Is a decimal value of 255. Okay, cool. Now, over here, when we do that with our value of DCC, check it out. Since we go right to left, it's going to maintain this value here. It's going to be the first 8 bits. Right there. And what is that? That is CC, matter of fact. So that's what's going to get preserved. And after that, we only did it for 1 byte. Check it out. We didn't preserve it for a whole 2 bytes. If I did 2 bytes, we end up with our original number, which means DDCC. Instead, we only do it for 1 byte. That means 0 for the rest for our AND operation, thereby eliminating everything else. So this allows us to exclude out the CC separate from the DD and leave it behind. Okay? So this way we extract just the CC. So we shift it over to the number value that we want, and then CC, and then we do the AND here. So we'll only keep that first byte there, and then everything else gets negated and taken away. You're probably going, okay, maybe I understand it, but why on earth are you telling me all this? Well, I'll tell you why. Because we're getting ready to do exactly that for extracting these numbers. So here we're going to shift this over 24 bits to the right. And the reason why is we need to get this first number, right? So that first number is in that first byte and it's hidden. And what's that first number? 192. It's hidden inside of this structure. So if I shift my bits over and it's 32-bit wide, right? So let's look at this. Okay, so it's 32 bits wide, right? And if we shift over 24 bits, guess what? We've eliminated all but the very last byte here, which is FF. So very cool. And that gets us pretty much what we want here. And so we preserve that last byte only. See, there's no need for me to do an AND because basically I've eliminated all the rest of this. So if this right here gets shifted over, so it would just be the first DD here. This DD would be shifted all the way to the very end, and everything else would get eliminated. CC would be gone, EE would be gone, and FF would be gone, and the only thing be left would be DD. And it would be zeros all the way across here. So that makes life easy. So that extracts that first number, which would be 192. And then we're going to do dot the next number. Now we need to shift it over 16 bits to the right. And then do, after we preserve that number, we do an AND, a bitwise AND operation, in order to wipe out the rest of the other values for the other bytes. So that means we need this one right here. It needs to be preserved. Alright, well, we already are over 1 byte. Right? So that's 8 bits that were already moved over. So it would be 1, 2, 3, 4, 5, 8. Okay. So right here's our next set right here. So this set right here is going to get shifted all the way to the end. But we still have this other byte sitting here that needs to be wiped out. Okay. Fair enough. Right? Or, did I count off some bits wrong? I think I did. Yeah, that's 4, and then... Okay, that's 4 there. Okay, yeah, so these would get eliminated, and then these would be preserved here. There we go. Now I'm seeing the pattern correctly. Okay. So this one gets shifted all the way over, and the rest of this all gets ditched right here. The highlighted one's going to be at the very end, and then we're still stuck with this left over. So then we're going to do our AND vertical bar. We're going to do our bitwise AND operation, right, to eliminate this first byte here. Because remember, we've already wiped this out with our shift 16 bits to the right, right? And this is 16 bits right here. So when we shift this to the right 16 bits, it will eliminate all this. And then we do the AND bit operation here. It only takes care of this first byte, remember, because this will be all the way over here now, and so it'll preserve that first byte, and then the rest will get, AND with the zeros, and this will wipe out the rest of that data, and will leave us with just that second number. And that second number, in this case, would be 168. See? So by shifting that all the way over to the right, and then we eliminate with the that's with our 16-bit shift, we'll move this all the way to the right, and then our AND with the FF here will preserve this number, and then do an AND operation with zeros to eliminate this number here. So this is how we extract that second number right here. Okay? Now we need to extract the next number in our setup here, which is going to be which number? Yes. In our case, it'd be 11 on this computer. Okay? Well, let's see how to do that. So what we need to do, we need to shift over 8 bits. Why? Because it's already in that position right there, right? Then the third position, third byte, already over. So since we're already in the third byte, right here, which is going to be this one right here, it's going to be our third byte. And because we're already in the third byte, we need to do what? We need to shift it over 8 bits, which would eliminate the very next byte here. So that moves that over here. Sorry, that moves that over here. And then we're going to do our AND operation. See, and our bitwise AND with our FF here. And that's going to do what? That is going to preserve this, because this is going to be moved over 8 bits. This number here is going to get preserved by our AND because it's going to be all ones, right? So when it does the bit operation with the ones here, it's going to preserve this number. But then it's going to do an AND operation on the rest of these other bytes here. It's going to eliminate it. So in this way we can eliminate all these values in here and convert them over to zeros. Okay, and so that will eliminate the rest of those and extract only that third number, and that's going to give us the 11 now. Awesome. Now let's talk about the last one. Now how do we get the last one? Now the last one, quite frankly, is the easiest one. Check it out. We don't have to even do a shift on it at all. We can just use our AND setup here altogether. Now remember, this last number here, 129, is in the last position. So just again, as we said earlier, there's no shifting needed. We just preserve it with our AND operation here, our bitwise AND operation with ones, and then eliminate, and it'll do zeros for the rest of the numbers. So essentially, what I'm saying is that we'll preserve this set of ones right here by multiplying, by doing an AND logic operation, bitwise AND operation, logic operation, shall we say, on all these different ones here, and then it'll be 0 for the rest, which will eliminate all the other bits and replace them with zeros. So that essentially extracts out our last number here. And that gives us the 129. And that displays it to the screen. And then that's how we get our 192.168.11.129. In our case on the other computer it was 32 for that last number there. So it was 192.168.11.132. And then we're going to also just display the port here. So I did a SDLnet underscore read 16 here. And then I said, and it read clients, IT here being our loop setup here. Let me talk about that real quick here. And clients, and arrow over here, IP, arrow again, port, close parentheses, comma, IT read clients, and then arrow here, read buffer. And that lets me just display that remaining value here. So very cool, and that will display this message that goes with it, whatever we read in from that client. So basically we're saying client, this IP address, this port number, and what they sent us on the server. Now you're probably wondering about this it read clients here. Well, where did that come from? Alright, well when we were setting up our loop up here, and hopefully I didn't jump too far down. Oh, I did. Yeah, so that'd be the same thing as I pulled down too far in the code. My mistake, sorry. It is the same as everything I was saying earlier for this host connected up here as it is for this other part, and we just go down to the port. Alright, so don't worry about the IT part. I'll get into that later. Sorry about that. But this right here covers us all the way down through our port, and I'm saying and here because I need to do a pointer referencing to client temp.ip here with our arrow for, remember, for our dereference, client temp.ip pointing to our memory address port inside that structure. Close curly brace, and that's how we're accessing that data. So remember, this is the memory address reference value. Star means the data, and symbol means memory address reference. Alright, so else here, fprintf. So if this doesn't work out, we need to, of course, if we can't get the pure address and it doesn't go the way we want, we need to get out an error message. So fprintf, open parentheses, std error, comma, and in quotes, SDLnet, space TCP, space get, space peer, space address, colon, %s/n, and then close quotes, comma, SDLnet underscore get error, open close parentheses, semicolon. And then that is going to give us our error message, if there is one, and it's going to be displayed, actually going to be stored into the standard error file. Now remember on Linux this would get displayed to the console instead. Next thing we need to do is add the new client to the end of our list of clients for our server. So everything went through successfully. We didn't have this error here. Great. Now we can do clients.pushback here, and then we need to use this .pushback operation in order to add some object to the end of our list. Now this is cool because we can add actual whole class objects or data structures from C or whatever. And so we're using a C data structure in this circumstance. So by me doing clients.push_back, this is going to add client temp to the end of the list. So it's going to add the new client that we just verified, worked out fine, everything, to the end of our list. Close parentheses, semicolon, everything's good, awesome, and now we need to actually add this to our socket too, for our socket set. Don't forget, we need to add, as we add, each client needs to get added to our socket set. So SDLnet _TCP _add socket, open parentheses, socket set, comma, client temp dot socket, close parentheses, semicolon. And this is going to add our new client that we just basically pushed onto our list to our socket set to check to see if there's any messages from that client. And again, it needs to be added to our socket set so that we can actually check it for messages. Okay, close curly brace. And then let's move on to the next part here. So very cool indeed.